Third video in which we're going to explore using inverse trig functions to solve for angles in right triangle application type situations. And since we're talking about right triangle applications, it's a good time to mention that often when we work with right triangle applications, we refer to angles that are called angles of elevation or angles of depression. Okay, so when you think of elevation, of course, you maybe think of lifting up from something, and to be depressed is to be down from something. But when we say each of these are angles of elevation or depression respectively, we're referring to an angle with respect to what we refer to as the horizontal, or the base word of horizontal would be horizon. Okay, and this horizontal is what we have in our heads is this imaginary line that runs level with the ground. So this would be considered like the horizontal right here. But I've included a couple of sketches over here. We'll say there's an observer, and they describe their being an object either up or down from themselves. We say with respect to this idea that this imaginary horizontal line runs through them, we say an angle of elevation is any angle up from the horizontal, whereas an angle of depression would be any angle down from the horizontal. And anybody who studied trig knows that when you sketch angles in standard position, angles that proceed counterclockwise are considered to be positive, and angles that proceed clockwise are considered to be negative. But for instances in which we're talking about application problems, it doesn't matter if it's an angle of depression or an angle of elevation. We always consider these things to be positive. So we're actually going to scratch this idea out of our heads when we talk about application type situations. So I think that when you read word problems, you see angles of elevation and depression, and it tends to confuse people. So that's what we're going to look at in this set of examples in this video. So let's start with example 3 here. We say swimming pool shown in the cross section, shown at the right, has a depth of 3 feet at the shallow end and 8 feet at the deep end. I kind of probably need to retype that one there. But you'll notice here that I didn't include the sketch. Actually, we're going to make a sketch of this situation. So when we talk about a pool, if we were to do like a cross section, we say here's our cross section of the pool. We're saying that the shallow end has a depth of 3 feet, and we say that the deep end down here has a depth of 8 feet. So what we're looking at is a situation where if we were to cut a cross section or look at the pool from the side here, you could see that this is what the pool looks like from the side. Okay, so of course pools drop off this way. What our job is to find the angle of depression between the shallow end and the deep end. So when we talk about angles of depression, here's what I want to keep in mind. We're imagining this horizontal that goes across this here. And when we talk about an angle of depression, we're referring to this angle down here. So we say this angle theta down from the horizontal. Well, you'll notice that we've created a right triangle here. And I think that in any instance where you have an application type of situation, resketching the right triangle off to the side is probably the best thing you could do for yourself. So we're trying to find this angle theta here. Okay, and we have this depth here. Well, this would be the original 3. If we were to slice that off of the 8 over here, we'll leave behind the 5. So let's put it this way. Pools are often, let's see, 25 yards, one length down. So that'd be 75 feet. Okay, I'd probably include that in the problem the next time also. But we say 75 feet. What we want to do is find this angle of depression. And we can actually do this now just by using inverse trig functions. We say, well, what trig function could we use to relate our angle to the side opposite and the side adjacent? So we have tangent. So we say tangent of this unknown angle is the side opposite over the side adjacent. And so we get this here. We say, well, then therefore, if we took the tangent inverse of both sides, tangent inverse, which will undo our tangent, and take the tangent inverse of everything on the right, we end up with this. We say theta is equal to the tangent inverse of 5 over 75. This literally says I am the angle that when you take the tangent of me, you get 5 over 75. But we'll just ask our calculators here. And kind of talking about this reasonably, it wouldn't be a very big angle, but we say 5 divided by 75, enter, making sure I'm in degrees mode now. We'll hit tangent inverse. We say about 3.8 degree angle of depression. So the angle of depression is about 3.8 degrees, which is entirely reasonable. Okay? Let's take a look at another example. As a matter of fact, this one does not start off with an angle of depression or elevation. It just says a historic lighthouse is 200 yards from a bike path. So we have this 200-yard distance here along the edge of a lake. It says a walkway to the lighthouse is 400 yards long. So we have a 400-yard long measurement here. It says find the acute angle theta between the bike path and the walkway as illustrated below. So this is not our angle of elevation nor depression. We just say it's an angle theta. And if we wanted to solve for theta, we'd say, well, which trig function would relate this angle theta to these two sides? That would be my opposite side and my hypotenuse. We say opposite over hypotenuse would be sine. So we have this now. We have sine of our angle would measure 200 over 400, or sine of the angle theta would actually be a half. So now to undo the sign, just as we would undo any trig function, we'll use its inverse trig function. So we say sine inverse of the left side. Those cancel out and leave behind theta. And this will equal sine inverse of the stuff on the right, which is 1/2. So we get theta equals sine inverse of a half. And so now we can just go ahead and ask the calculator. We say, dear calculator, 1 divided by 2 should be 0.5. We'll do the sine inverse of this. We say we've got a 30-degree angle, which, you know, if you think about it, makes sense. This would have to be a 30, 60, 90-degree triangle, because looking at the short side, if we say that this is some distance x, then the hypotenuse would be twice that distance there. And of course, over here, this would be 200 root 3, if you care to just write that down. But what I'd like to do now is this, you know, we'll kind of extend this problem. What if we said that this, we notice that the lighthouse is casting a shadow. And let's say it's casting like a 100-yard shadow, just for the heck of it here. We could redraw this situation. So we say, here's my lighthouse here, and the dome at the top. And let's say the sun's up here, and we're casting a shadow. And the shadow happens to be 100 yards long, and we have an observer down here. So our observer, what they do is somehow with maybe a sextant, which measures the angle of things rising up into the air, actually, maybe they don't know the angle. That's the whole point of this, I guess. They don't know this angle here, but they're already aware that this lighthouse, let's just say, is maybe 150 yards tall. So maybe our goal is to find the angle of elevation here, the angle up from the horizontal. Okay, so to do this, we could use tangent. It looks like we have the opposite and the adjacent side here. So we say tangent of this angle of elevation is 150 over 100. So theta would equal the tangent inverse of this on the right side. So 150 over 100, which could certainly be reduced. But we say theta is approximately, let's see here, 150 divided by 100. 150 divided by 100, of course, is 1.5. But we'll just go to show it here, 1.5. We'll do the tangent inverse of this, and we get about a 56.3 degree angle. So 56.3 degree angle of elevation. But yes, when we talk about angles of elevation, we're talking about up or down from a imaginary horizontal line that we consider to be the horizontal. Cheers.